Ladies and gentlemen, in the construction and operation of nuclear power plants, the radioactivity of the heat transfer medium imposes quite inordinate demands on the tightness, clean lights, deactivation and reliability of the heat transfer installations. The problems are especially acute in plants where the heat transfer medium is circulated at high pressures. When the many questions of weight, manufacturing technique, transport and assembly were subjected to an economic analysis, it turned out that the usual huge steam generator units are not really suitable for this purpose. Preferable by far are sectional units where the section diameters successively diminish as the pressure of the transfer medium increases. Apart from being lighter and easier to produce, these units do away with many of the problems otherwise associated with the thermal expansion of the whole assembly and of its individual sections. The first Czechoslovak nuclear power station with an electrical output of 150 MW employs natural uranium fuel, heavy water the moderator, and carbon dioxide as the heat transfer medium. Its sectional steam generator was designed to permit batch production of the sections, to facilitate their transport and assembly, to simplify the thermal expansion problems, and to allow easy removal of each section separately for repair or replacement. Before the sections were put into fuel production, a complete unit was tried out in pilot plant operation, running on inactive carbon dioxide under the fuel service load. This enabled the designers to adjust the system, fix the requisite size of the heat transfer surfaces, ascertain the hydraulic resistances, and so on. The carbon dioxide leaves the reactor at 57 atmospheres and 425 Celsius grades for the double pressure primary steam circuit on the steam generator. The intermediate pressure steam, which leaves the steam generator at 32 atmospheres and 400 Celsius grades, is mixed with low pressure steam of 2.2 atmospheres and 185 Celsius grades beyond the first stage of the turbine. The station has a total of 6 steam generators, figure 1, each pair feeding 150 MW turbo set. Each generator comprises 3 parallel units encased in airtight thermally insulated sheet metal housing and provided with dosimetric extraction points. Every unit consists of two parallel branches of 13 U sections apiece. Each of these U sections, figure 2 and 3, sheeted in a tubular jacket of 159 mm diameter, contains 1922 mm tubes anchored in tube plates at its ends and held in position by spacer grids. The tubes carry water or steam, while their outside surfaces are swept by a countercurrent of hot carbon dioxide. And their arrangement ensures that both forced and natural convection will take place in the same direction. The U-bands allow free thermal expansion both of the individual tubes and of the section as a whole. The sections thus form compact and versatile assemblies which are easily amenable to modern batch production methods. Figure 4 shows the test rig for functional checks of these sections and research into their parameters. On this rig, several fuel-size prototype sections are resiliently mounted in a way closely resembling their installation in the actual steam generator. They are connected up in a heat exchanger loop and heated by gas burners. The equipment runs under actual service conditions on non-active carbon dioxide. The circulation blowers are encapsulated together with their drive motors to ensure that no carbon dioxide will escape and no oil enter the heat exchange circuit. The work done on this rig also covered the emergency systems and other auxiliaries, especially of the primary steam circuit. The emergency dump condenser evolved to deal with leaks between the gas and the steam water sides is shown in figure 5. Installed on the test rig at the same level at which it was mounted in service. In a remote controlled and monitored experiments, leaks were deliberately induced in the system and the penetration of carbon dioxide into the water was measured by infrared analyzers. In the power plant itself, the emergency system is augmented by dosimetric checks and by filters which intercept particles of corrosion products in the ducts to the circulation blowers. The range of detailed design and production problems that had to be overcome in the development of these units is best illustrated by two examples. A vacuum leak detector had to be aware to check any seepage of gas from the primary circuit to the atmosphere or to the secondary circuit in the production and assembly stages as well as in service. On the other hand, a great deal of research into the effect of thermal shock and sudden expansion was necessary to perfect a production technique which finally reduced the influence of these factors to a minimum. A crucial operation in the manufacture of the steam generator sections is threading the jacket over the bundle of tubes. This is done in the cold state and without any welding on the tubes themselves. Special equipment had to be devised, including a single-purpose tube bending machine and the assembly jig shown in Figure 6. Strict quality control is imposed throughout the manufacturing process to ensure rigid adherence to the specified technological conditions. The tube surfaces which are to come into contact with the carbon dioxide are treated so as to remain metallically clean even after the final assembly. All the valves are subjected to X-ray inspection. Tightness is checked by vacuum apparatus on the gas side, and all the sections are tested for leaks before installation in the composite units. Figure 7 shows a box of steam generator unit during construction. Further work is now in hand on steam generators for atomic power stations working with higher gas pressures and with other types of heat transfer media. Thank you.